Hello everybody. In our last lecture we had a question that how we can represent negative numbers. So today we'll try to answer this question that how negative numbers can be represented, and also we'll try to answer the second question that if negative numbers can be represented, then how addition, subtraction or other binary calculations can be done. So let us start thinking in a way that how do we represent it in a decimal numbers. A negative number in a decimal representation, we represent it by putting a negative sign. So can we put the same negative sign in binary numbers? Possibly no, because whenever we are going to use binary numbers, they would be in a digital word, and in a digital word only understand the language of zeros and ones. So that means my negative number or that negative sign has to be represented in form of 0 or 1. So let us think of some strategies how we can represent a negative number using zeros and 1. So one possibility, one naive possibility I would say, would come to our mind that we can represent, we can leave one particular bit as a sign bit. So that kind of numbers I'll call sign magnitude negative numbers. So here one bit, which bit to be choose? So let us say most significant bit. Let us say most significant bit is designated now to represent a sign bit, and 1 would represent negative and 0 would represent positive. So this could be one easy sign representation. If we see this method, this is good. So let us say we have a 8-bit binary number and I want to represent minus 35. So if I want to represent minus 35, so I can put 8th bit or most significant bit or leftmost bit as 1, and remaining 7 bit I can use to represent 35. Fair enough. So 35 means 16 32 plus 3 plus 1, 32 plus 2 plus 1 is 35. So I can represent minus 35 using this. And similarly, if I have to represent any number like positive number 127, so my most significant bit is 0 because the number is positive, and rest of the bits I can use to represent that number. So with this way we can clearly see the range of number could be minus, for 8-bit number it could be minus 127 to positive of 127. So it looks good, intuitive, and it looks to work also, but there are few challenges here. One challenge is that there are two zeros. One, that in this is a negative zeros, because the sign is minus. 1 represent minus sign, so this particular representation is a minus 0 and this particular representation is a plus 0. So having two zeros is complicated. We'll see how. So the other thing is, let's say I need to do some arithmetic here. So what I need to do is I need to see whether a sign bit is same or not. Let's say I want to do addition. If sign is same, then I have to add. If signs are different, then I need to subtract. Similarly, if it is a subtraction, then first I need to change the sign and then figure out whether it need to be added or subtracted. Okay, so and addition and subtraction otherwise can be done, like we remove the sign bit. So the how the process would be, because sign bit has a special meaning here and the rest of the number is a magnitude number. So if I need to subtract these two numbers or add these two numbers, so this is a negative number and this is a positive number. So what I need to do is I need to subtract this positive number from the negative number. So essentially here also I need to see that which number is a bigger number. If magnitude of this number is big, magnitude of this number is here, magnitude of this number is big, so that's why we are subtracting this from this number from this number. And subtraction we have learned in our previous lecture, so we do the subtraction that way, and then we get this result. So whatever result we get, after that we add the sign bit. So sign bit would be added based on the calculation. So because whatever number we found is a bigger number, so a sign of that number would prevail. So this is how subtraction and addition would happen if the signs are different. Okay, so here now finally we have added this sign bit of 0 because this number was a bigger number. Okay, so there are couple of steps involved. It overall, in summary, I can say these steps are: first I need to find out which I have to first remove the sign bit, then find out which number is a bigger number. If subtraction need to be done, then we need to do subtraction using the subtraction method. Okay, and then after that whatever result is achieved, then we have to find which is the sign bit of the result, and then catenate that or add that result bit in the MSB, and then that's the final addition. Similarly, if subtraction has to be done, then again, if signs are different, then we need to subtract. If signs are same, then we need to subtract. If signs are different, then we need to add and then find the corresponding result of the sign bit. So overall process is little clumsy because here we are doing like we first of all require a different hardware for addition and subtraction. So, and we don't know which hardware is required. You need to require both adder, subtractor, and a controller which is determining when to do addition and determining which sign bit is required. That is additional steps. So along with this arithmetic confusion, there is also additional confusion because of two 0 bits. So two representation of 0. Can we have something better? So let us think of some other naive representation. So let us say we are representing it in a ones complement manner. Ones complement means we are taking the complement of that number. Let's say if u is a number and I need to find out the negative of that u, then what I do is I will flip all the bits. That means if the bit was 0, I make it 1. If bit is 1, I make it 0. So that way a flipped number is a negative number. That's my assumption, and this particular representation I am calling ones complement representation. So because for positive number we assume that MSB, most significant bit, is 0. So because we are flipping, so last bit or most significant bit is 1, that means it is negative, and if most significant bit is 0, then it is positive. And n-1 bit would represent magnitude. So in a way this is very similar to sign magnitude, that one bit is reserved for sign and rest n-1 bit is representing magnitude, but the order is different because we are here inverting the bits. So let's take some example. Let's say this is plus 13, 0 0 0 0 1 1 0 1, it's in 8 bit, and then minus 13, it is simply inverting all the bits, 1 1 1 1 0 0 1 0, or similarly any other number. So essentially receiving or getting a negative number is easy. I just need to flip all the bits or reverse the polarity of all the bits. And because I can represent n-1 bits of magnitude, the range of the numbers would be minus 2 to the power n-1 to 2 to the power n-1. So I can represent minus 1 to 2 to the power n-1. So for example, if it is 8-bit number, I can represent minus 127 to 127. So this is the number of bits I can represent. Here also we see that we have two zeros. So before that, let's also see the mathematical background. So when I am flipping all the bits, it is also equivalent to subtraction from 2 to the power n minus 1, because 2 to the power n minus 1, so let's say the case is 8-bit number. For 8-bit number, the 2 to the power n will be 256. 256 minus 1 would be 255, so that means all ones. And if I want to get a negative number, so what I am essentially doing, inverting of all the bits, which also means I am subtracting from 2 to the power n minus 1, and I am subtracting this u, or basically magnitude of this u, from the 2 to the power n minus 1. So this can be, we can say this is the mathematical representation of this this number, negative number. Now here also there are two issues. One issue is I have two zeros. One I call positive 0 because sign bit is positive, and the other is a negative 0 which is invert of all these zeros. So this is a negative 0. Addition and subtraction, if I am doing it on only positive numbers, then it mostly works. If I am doing only with the negative numbers, then also it works. But if I am doing addition and subtraction using regular arithmetic or regular binary additions, then if one number is positive, one number is negative, it doesn't work. So for example, here if you see, this particular number is 13, and this particular number is 1. If I invert this is 1101, so that means it is also 13. If I am subtracting 13, I am adding positive 13 and minus 13. If I add plus 13 and minus 13, let's see the output. 1 plus 0 is 1, 0 plus 1 is 1, and similarly all the ones I am getting. So minus 13 plus 13 is equal to minus 0. Still okay. Still okay, because at least it is giving me 0. But on the other hand, let's say consider another number. So this number is minus 13, this number is plus 13, and this number is minus 12. So if I am adding minus 12 and plus 13, the output is 0. So that means there is, this particular output is wrong. So addition works for a negative number, or like adding two negative numbers or adding two positive numbers, adding negative and positive numbers will mostly work, but it doesn't work in some cases. So because it doesn't work in some cases, this particular condition is not good at all, because we believe computer is supposed to do everything correct functionally. So that means we need to find out some other representation which is better than this, which doesn't create this confusion. And this particular error came essentially because we have two representation of zeros. One representing all zeros, another representing minus 0, that means all ones. So because of two representation of zeros, we are getting this correction error of 1 in some cases. Okay, so what can be the other method of representing negative numbers? Another alternative we can think of is we can add a bias. So everything is positive in our numbers. So let us say if I want to represent any number, I add that some particular bias. And for example, let's consider that for 8-bit number, I add a bias of 127. Okay, so if I'm adding a bias of 127, let us see how it works. So I want to represent 1. I want to represent 1 in binary. So first thing I need to do is I need to add 127, so it becomes 128. Now I will represent this 128 in regular binary. So that means 100 0000. Okay, so similarly for any other number, if I want to add, I want to represent in binary, then first I need to add this offset or this bias. For example, I want to represent minus 127. So first I need to add bias. So minus 127 plus 127 will be 0. So that means if this number is there 0, it actually represents minus 127 in bias mode. So in a bias representation. Similarly, if I want to represent plus 128, the output would be 128 plus 127, that means 255, and 255 can be represented using 1 1 1 1 1 1 1 1. Okay, so there are couple of observations here. Now if I want to represent any number using biased method, then for every, like if my number is 6 bit, 7 bit, 8 bit, bias has to be defined. It should be known to everybody who is doing computation. Okay, so it's better to standardize a bias if I'm using a bias method of representing negative numbers. The other thing is, for representation sake it is still okay, but if I need to add or if I need to subtract numbers, then I need to take care of bias, because let's say I am adding two numbers. So f u plus v, u and v are two numbers, I want to add two numbers. So the biased number, this fu is a biased number, this is also biased number, because bias is added here as well as here. So if I want to add two numbers, I need to finally subtract bias out of it. So this representation using biased method, even for addition or subtraction, I have to, in case of subtraction I have to add bias, in case of addition I need to subtract bias, then only I can get actual addition or subtraction. Okay, the other thing is, let's say the number is 6 bit, number is 5 bit. For 5 bit number bias would be different, for 7 bit number or 8 bit number bias is going to be different. So this bias, further, as I said earlier, it should be known whenever we are doing any kind of arithmetic using this biased negative numbers. Okay, this also looks crude, although we have solved one particular issue with this, that 0 will have only single representation, but because addition, even addition and subtraction would require additional step of adding bias or removing bias. For multiplication it's even more difficult. We won't be able to use this biased method for doing multiplication. So this leave us at a crossroad, that we are not able to find intuitively how should we represent negative numbers. Okay, so to find out the solution, let's go back and see that why it is so challenging, or what are we actually looking for. What should be the ideal representation of negative numbers? So one thing we would like is it should be simple. Okay, two representation of zeros will give unnecessary hustle, and the results are not desirable because it will create at least some confusion. The other thing, addition and subtraction should be easy, and it would be, because we are talking of a digital design or a digital hardware, it would be even better if addition and subtraction both can be done using a same hardware. Okay, or in a same method. Because we are sometimes adding numbers, some of them are positive, some of them are negative, adding negative and positive numbers. So that's why if there is only single method of addition and subtraction, that will make our life easy. Okay, so again, to look at things, let's look at another representation of numbers that may help us in understanding how should we represent negative numbers. So this particular method of representing number is called number circle. So let us say we have 4 bit. I want to find out 4 bit numbers. So I would like to represent, I can represent it like a circle. So how do I write this, create this circle? Because I want to create it using a 4 bit. So I will first of all write 4 zeros, that will be the top of this circle, and every increment will give me in a clockwise direction next number. So increment from 0 to 1 is next point in the circle, 1 to 2, 2 to 3. Similarly, every addition is giving me a circle, and when I reach 15 and again add 1, then it will become 0. So there is a discontinuity here. Okay, so this discontinuity is also called breakpoint, and if this essentially, this also means that I cannot represent any number bigger than 15 in a 4-bit representation. So this is also called overflow. So there are a couple of more things here. First of all, I am moving in a clockwise direction. If I want to add, let's say I want to add 4 to any particular number, I want to add 4 to 1. So I will go 4 steps in a positive direction. 1, 2, 3, 4. And let's say I want to subtract. Let's say I want to subtract 4 from 12. What I will go is, I'll go 4 steps in anti-clockwise direction. So in anti-clockwise directions I go. So 11, 10, 9, 8. So after 4 steps I got 8. I got at 8. So this is what it is. But if I crosses this particular line, which is a line of discontinuity, then a result will not be correct here. Here, at least in the positive circle, the results will because we are reaching a condition of overflow. So let's say I want to add 4 to 14. So because I have crossed this particular circle, 14, 15, 0 and 1. So I will get an output of 1, but because it is crossing this particular line of discontinuity or line of breakpoint, so I would get an overflow condition. Or similarly, going in anti-clockwise direction can give me a underflow condition. So this particular diagram has been taken from this website, which we'll visit after a couple of slides. So can I take some clue from this number circle? If I represent in such a way that let's say, so that I can represent some negative numbers also. Okay, so in case of negative numbers, what I am doing is I am trying to do in the same way that going clockwise will give me correct results, going anti-clockwise will also give me correct results. So let's say I want to subtract 4 from 2. I want to subtract 4 from 2, so I'll go in a negative direction or in a anti-clockwise direction, 4 steps. 1, 2, 3, 4. So subtracting 4 from 2 is giving me minus 2. Similarly, if I am adding 5 from minus 3, I am adding 5 to minus 3, then I am going in clockwise direction because I am doing addition. I am going 5 steps, 1, 2, 3, 4, 5. So adding 5 to minus 3 is giving me 2. So this means this number circle, if I represent in this way, it can give me some good characteristics. That it's an intuitive or a standard representation. Okay, so we understand clockwise means addition and anti-clockwise is subtraction. So this is at least one observation we got from here. The other observation we can see is if I want to see I want to get a representation of plus a number or minus number. So let's say I want to see plus 4. So what I can do is I can do a right clockwise direction from the 0, 1, 2, 3, 4. It gives me this particular number. Okay, so that means this is the representation of plus 4. So similarly, if I go in an anti-clockwise direction from the 0, then it will give me minus 4. -1, -2, -3, -4. So if I put my numbers in this way, so we are all talking. I'm right now talking only in the decimal form. In the decimal form, along with the decimal form, we can look at the binary also. So that means 1 1 1 1, adding 1 will give me 0 0 0 0, and this addition is all correct. Okay, but adding 1 from 1101 will give me 1100. If I add 1 to this number, then it would be 1101. So that means again it's a natural representation that adding 1 in a clockwise direction is giving me correct results. And there is only one representation of 0. Discontinuity would happen here. Okay, so discontinuity would happen here. So if I am crossing this particular line, so let's say I am adding 1 to 7, then it will give me 1000. Because I am crossing this line of discontinuity, then this would be an overflow condition. So because 1000 does not represent 8, but it represents -8. Okay, 8 is essentially out of bound for this particular representation. For 4-bit number, the number range is a 7 or -8 to 7. So whenever I cross this particular line of discontinuity or a line of breakpoint, then there would be overflow or underflow. Overflow if I am going in a positive direction, and underflow if I am going in a anti-clockwise direction. Okay, the other observation here is let's say I am taking u steps or some x steps in clockwise direction. Let's say I am taking 4 steps from 0 to 4 steps here. This also means the same thing can be achieved by going anti-clockwise in 12 steps, or 2 to the power n minus u anti-clockwise steps are equivalent to u clockwise steps. So let's remember again, clockwise means we are adding u numbers, adding a number u, and anti-clockwise means we are subtracting number u. So that means if I can represent addition and I can represent it using subtraction also, that means here addition can be represented using subtraction. That's a very magical property this particular circle has. So because now addition can be represented using subtraction, so that means I can do addition using subtraction or subtraction using addition. This makes my life simpler, easier. There would be only single representation and there would be only single way of adding numbers or subtracting numbers. Okay, so I'll quickly break this presentation to see this number circle, and then we'll get back to this presentation.